Het ziet er goed uit. Het ziet er goed. Mooi uit. Oké, dat gaat beter. Okay, students, it's 1:45 on a Tuesday, 16th of February. Welcome to the first real lecture on multibody dynamics. Looking outside the window, I see all the snow and ice has gone, unfortunately. It was a beautiful weekend with a lot of ice skating. I hope you all survived and didn't go under the ice. At least I enjoyed. Okay, multibody dynamics. Today's topic is Newton-Euler equations and constraints, in particular free body diagrams, and all the material is in chapter 10, and I'd like to give an introduction of that in this first hour. And again, the second hour will be questions and answers in Zoom. Okay, so let's dissect the title, Newton-Euler. So the first part is Newton, right? So what is Newton? What is this Newton thing? Oops, go back. Here we go. I have to connect my pen, sorry for that. Okay, now, pen is back. Oh man. Technology. Okay. Okay, here we go. Yeah. So the first part, the Newton part. What are we talking about then? Oh, wow, it dropped out. Oh, why did it drop out? I'm sorry for all this technology mishap. Okay, there we go again. Screen mirroring. Yeah. Go. Okay, now we're back. Okay, first part, Newton. Well, what is in equation of motion, what is a Newton? What are Newton's laws? Well, we say the sum of the forces equals mass times, yeah, you would say acceleration, but I would like to say is mass times the change in velocity with time. And then, what is velocity? Well, velocity is defined as the change of position with respect to time. And of course, most of you know it as the sum of the forces equals mass times acceleration. Well, I say on purpose mass times the change in velocity because he has these three laws, and which we will all see today. And then one of the laws is if there's no force, then there's no change in the velocity, right? So therefore, some forces mass times change in velocity. And velocity can change in two ways. It can change in magnitude, and if we talk about velocity in different directions, it can also change in direction, and we will see that later on. Okay, for what type of objects did Newton formulate the law? And then the audience would say, for apples, right? Yes, so of course he was under the apple tree, and there he was seeing that an apple was falling down, and that was under an act of gravity, and well, apparently that was not what he had in mind. In mind, he had another type of spherical object, and actually a bit larger than the apple. In those days, everybody was totally intrigued by the motion of the heavenly spheres, the things outside there. And what are the heavenly spheres? Well, one of them is, for instance, the sun, and the other one is, for instance, the earth. And the big question is, why do they move as they move? Or in other words, why does the earth go around the sun in, well, how long does it take? What is the the RPMs are rounds per minute. No, it's a round per year, right? It's one round per year. And of course, about its own axis, it's rotating, but that's not the purpose for today. So the Earth is going around the Sun. And why is it going around the Sun? Why is not the Earth just moving along? Because there should be a force, because the velocity is changing. Well, then the force he was discovering or defining was a thing called gravity, right? So gravity is the main thing, and what was his gravity law? He used, of course, all the observations done by Tycho Brahe and by Kepler, and so he had a lot of experimental data. He didn't have to take that themselves. He used that of others. And then what is the gravity law in this case? Well, it is that the force, and again here is a Newtonian law, because this force pulling on the Earth is the same as the force pulling on the Sun, the gravity force, and they're equal in size but opposite in direction. And that's law 1, 2, 3, I don't remember which one. Check that out. Well, it has, how big is the gravity force? Well, it has something to do with the mass of the Sun and the mass of the Earth, and it's linear in both. It has something to do with the distance. The farther away you are, the weaker is the force, and it's r squared. And my son explained why it's r squared. Yeah, because it's you could see it like a circle, right? Which enlarges then, or something like that. I don't know. Anyway, I still find it intriguing that it's r squared. And then there's some constant gamma. Now, of course, we don't know this law as posted right there, but we know it in a little bit different form on Earth. When we Earthlings think about this, then how do we think about gravity? Well, we say, oh, gravity is mass times gravitational acceleration, right? That is, but that's actually a force, of course. That's F gravity. And then if you compare that with this, so apparently if we pull out our own mass, then we are stuck with capital M gamma over r squared. So apparently this guy is what we call gravity, the acceleration of gravity. And you can check out the numbers and that sort of works. Well, is that correct then? Well, it's almost right. As long as v is small, then it's okay. And small compared to what? Well, there's one constant velocity in nature, and that is the speed of light, c. So as v is small with compared to the speed of light, so c is speed of light, and then it's okay. And the speed of light is approximately, I don't know by head, what did I write down? 10 to the power 8. I have no clue how big this number is. 10 to the power 8. I don't know, a lot, large. I guess I will never go that fast in life. Anyway, very fast, and as long as it's smaller than that velocity. If it's not, then you have what we call Lorentz contraction, or then we have to take that into account, and all the laws are then scaled with this kind of number, v over c squared. Well, you see already, if v is small compared to c, then it's also about right. Okay, that was the Euler part. But there's a second name here. That's the Newton part. There's a second name here. That's the Euler part. So let's look at the Euler part. What is Euler? Euler. Question mark. Well, we are talking about rigid bodies. And rigid bodies have some extent, right? It's not the point mass. They have some form. So a rigid body. And a rigid body also has an orientation, so meaning you can draw a line on the body. For instance, let's say here's the center of mass, and you can think all the mass is there, but then you can draw a line on that. And then after some motion, the body can be in another configuration, right? So let's do that. Oh, I enjoy this copy. And then rotation is on, no scaling. And then I just move it here, and I want to rotate it. Hoopla! And you see suddenly that not only did the position change, but also the orientation of the thing, right? And that we see that because of this line, and we usually denote that by an angle. So in reference to this, we say, oh, there's an angle phi here, by which the body rotated. Now, the linear motion, that can easily be described with these Newton equations. Some of the force mass times acceleration into Cartesian directions. But then, how do we describe the orientation, the change in orientation? Well, let's start with this Cartesian coordinate system, so x and y. And let's take an inertial frame. Remember from the advanced dynamics, with some curly letter, n is usually the inertial frame. It's fixed to the ground, and of course the ground is Earth, and Earth is also moving, but well, we Earthlings, our mass is compared to the mass of the Earth is very small. Or in other words, the mass of the Earth is so large compared to us that we can say, oh, in comparison, for us it's like a stationary object. Of course, the Earth pulls on me and I pull on the Earth, but the Earth will not really notice that I'm pulling on it. I guess, I hope. Anyway, so inertial system, Earth, orientation, and how does that work? Well, we say that the sum of the torques around the CM, so here's the center of mass, is equal to, and then we have a magical thing, a mass moment of inertia times the angular acceleration. And this guy we call the mass moment of inertia. And isn't it nice that you hear all kind of things you already know? That is the most beauty. Read Alice in Wonderland on that. So mass moment of inertia, and what was the mass moment of inertia? There was a definition for that. Mass moment of inertia at the CM is the sum of all the particles times the distance squared with respect to the center of mass. So you just look, where is all the mass? I take a piece of mass, I calculate the distance, square it, add everything up, and then I get the mass moment of inertia. So that is how inert for rotation is a body. And as an example, let's take a simple body, a dumbbell. So this is a dumbbell. So we have a mass here and a mass here, and the distance is, well, for simplicity, let's call this 2L. Then where is the center of mass? Well, the center of mass should be here in the middle, exactly, right. And then what is the mass moment of inertia? Well, that's mass times distance squared, so that's ml squared plus ml squared. So in this case, it's 2ml squared. So that's super easy. And for anybody, you can do that. It's just some integral which you have to solve. Okay, so let's recap. So for one rigid body, let's take this inertial frame again, x, y, inertial frame. We have this one rigid body. We have a center of mass here, Cm. At the Cm we have a mass and we have a mass moment of inertia. And then we have all kind of forces acting on the body, F1, F2, well, Fn you could say. Then we have, of course, a position of the center of mass. We have an x and y, but we also have an orientation because we put a marker line on the body to note how is it rotating. Then the equations of motion, EOM, for the thing R, and we can say in vector form, but well, let's say the sum of the forces equals the mass times the accelerations, and the sum of the torques about the Cm is the I of the Cm times the angular acceleration. And this is what we call the Newton-Euler equations of motion. And that is actually the whole backbone of this discourse. That is our apparatus, what we are going to use to solve all our problems. Now, to demonstrate the usage of this, we need problems, right? Otherwise, yeah, what do you do with the equation? Oh yeah, wow, nice equations, let's look at them. No. So we need a problem. And as an example problem, I want to look at the following thing. An example problem would be the following thing. It's a simple, we like simple things, simple 2D manipulator. And you may have looked already in the book and you've seen that the first part is really all about 2D dynamics and not 3D. Why? Well, to get to know our toolkit, it's sort of handy to start in a simple world, in a simple two-dimensional world. And by that you then will learn your toolkit, and if you know your tools well, you then can also apply them to the three-dimensional world, because it turns out that in the three-dimensional world all kind of strange things happen. In space it's strange, and the main thing in space is strange is rotation. So translation is okay in space, but rotation is very magical. Okay, but let's stay by the non-magical thing now. A simple 2D manipulator, and as it happens, I have such a manipulator here, and this is it. This is my simple 2D manipulator. So it's one arm and another arm. Forget about the hand. Chop off the hand like this, and then we have one arm and another arm, and they're connected at two rotational ends. And I'm rigid. I'm inert, right? So this is a manipulator. I can move on a two-dimensional plane with this thing. So what else? The manipulator, right? And this is the. Oh, I need a nose. Where's my nose? I need ears. Yeah. And feet, of course. I need feet. Well, this is my simple 2D manipulator. And our model then of this thing is like this. So we have, it's grounded, and then we have the first arm, and then we have the second arm. We call this a double pendulum. Why? Well, this is the first pendulum, and this is the second one, and they're in series, right? So the double pendulum. And then we are interested in the motions of this under the action of forces. Okay, yeah. This is the sketch of the thing. Let's make the complete sketch of the thing. So meaning we have one rigid body, and this is the second rigid body, right? Connected by hinges, and this is connected to inertial frame. So let's put that frame there. X, Y, inertial frame. Then let's give it some, oh yeah, there's a center of mass, of course, of every body. So and this is body 1, and this is what we call body 2. What else do we need? Yeah, we need to have names. So body 1, body 2, we call this hinge A, hinge B, and this is the end effector C. What else do we need? We need, yeah, positions, of course. This body has position x1, y1, and phi1 at the center of mass, and this one has x2, y2, and phi2. So apparently we have 6 coordinates. Then how do we measure the angles? Because we haven't been very clear about that. The x and y coordinate is clear. So actually the angles are measured like this. So this is phi1, and this should be then phi2. So anti-clockwise with respect to the horizontal axis. Then of course the thing has an extension, has a length. This is called L1, and this is called also a length. We call it L2. What else? Oh yeah, there's of course mass. So this is M1 and I1, and this is M2 and I2. Now, if there are no forces, so then nothing will happen, right? Then if it's moving, it will keep on moving, and if it's stationary, it will stay there. So we need forces, so we need gravity, And for now I'm going to put the gravity horizontal. Yeah, why not? I mean, it's all a model, so you can turn your thing around, and then you can say, oh yeah, this problem I know. Gravity is down, but then the x is down and the y is to the right, and I find that confusing. So this is sort of a handy way of operating. Oh, I have to resize my screen. Why does that resize? Oh, because I tilted. Yeah, of course. Stupid me. Let me get that back. Get back. Yeah, and then a little bit to the right. Yeah, that's good. I'm happy with that. Yeah, so so gravity is in that direction, and then we have all positive x and y, and I'm kind of a positive person, so I like positive things. So everything is positive now. Angles, positions, forces. You could put gravity there, and you could also say, oh yeah, so apparently there's an applied force, and maybe, so it's sort of double trouble, but for now, to be super clear, I say, oh, here is an applied force, m2 times g, and here's also an applied force, m1 times g. Actually, you shouldn't have both, you shouldn't have this and this, but it's for now just to be super clear. Okay, what are we interested in? Well, we want to know the motion, meaning, so this is the problem, what do we want to know? Well, I want to know x1 as a function of time, and y1 as a function of time, and phi1 as a function of time, to see how that thing is moving, and the same for body 2. So I just want to see this as a function of time, moving around. Now for some notation, we like to think in not in scalars. Up until now we used only scalars. We like to think in vectors. So we have a vector x, and the vector is x1, y1, phi1, x2, y2, phi2. Similarly, we have forces, applied forces, and those are f x1, f y1, m1, f x2, f y2, and m2. So we have forces, and in our case even we know what the applied forces are at the center of mass. So in the horizontal direction we have m1g, 0, no torque, m2g, 0, no torque. And what these are, we don't know. We want to solve that. Now how are we going to solve it? Solution. Well, apparently we need a Newton-Euler equation of motion. So Newton-Euler. EOMs. Why EOMs? Why plural? Well, because it's for both bodies. But so we need for both bodies to write down some of the forces is mass times acceleration, and some of the torques is mass moment over inertia times angular velocity, and that we do for body 1 and body 2. Okay. Yeah, but body 1 and body 2 are connected, right? Apparently, there are also forces from in the hinge from body 1 acting on body 2. And there are also forces from the ground acting on body 1 in the hinge A, because otherwise the thing will just fly apart. So, although I said we know the forces, yeah, we know the forces at the center of mass applied, but we do not know what these forces are. So, if we identify these as rigid bodies, we sort of cannot directly solve that. And so, to solve that, we need a strategy. And the strategy we're going to use is an old one. And it's the Napoleon way, I would say, Napoleon way. Maybe it's even older. And the Napoleon way is, the Romans already did it, or the Chinese, or I don't know. It's called divide and conquer. And actually that's what we're going to do the whole course around. Every time when we have a problem, and it looks too complex, we say, well, can we not chip it chop it into parts which we understand, solve those parts, and then connect everything again. So divide and conquer is our strategic way. How are we going to do that with our double pendulum? So if this is the double pendulum, this is one and this is the other one, how are we going to divide? Well, first of all, our mechanism to divide is the most powerful instrument of the engineer. And the most powerful instrument of the engineer is called, everybody has it on its desk, I think. This is the most powerful instrument of the engineer. Scissors. Now why do I say scissors? Well, with those scissors, what can we do? We can divide the system. So, of course, you can cut it here or you can cut it here, but that's not a very smart move because then we get a lot of more bodies. It's sort of smart to cut it here at these joints, right? So, let's go back. We say, no, I'm not going to do that. We're going to cut it here, and we're going to cut it here. Yeah. And by cutting it up, we now have two separate problems. So, let's cut it up. First of all, we have the support here. Then we have this first body. And then here we have the second body. Okay? And of course, on body 1 at the CM, we have this applied force, M1G. And at body 2, we have this M2G. But, as we said before, when we make these cuts here, then there are apparently forces here, otherwise it will not stay together. And similarly here. Now, there are no torques, but there are forces there. And which forces? Well, we don't know. Unknown joint forces. So this was point A, right? And this was point B. This was C. So we say, well, apparently there's a horizontal force in A here, and there's a vertical force in A here. And likewise, there's this vertical force in A on the support, and there's this horizontal force on the support. Same like here, body 1 is acting on body 2 by a horizontal force here in B and a vertical force here in B. And again, that same force, vertical force, that's the W, vertical force in B and a horizontal force in B. Now, without talking about it, I applied already a Newtonian law here, because I said action equals reaction. And likewise here, action equals reaction. The two forces are equal in magnitude, but opposite in direction. Okay, so this is now a free body diagram. This is a free body diagram. This is not a free body diagram, right? This Earth thing. But on purpose, I draw it to see where all the forces come from. But this is not a free body diagram. Why not? Well, because there's this whole lump of mass behind it, and there are also maybe applied forces to that. But anyway, here we have two free body diagrams. And now with these two free body diagrams, we can apply the Newton-Euler laws and derive then these 6 equations of motion for the bodies, for each body. So let's start. So for body 1, we're going to write down sum of the forces equals mass times acceleration, which then in 2 directions, right? So that breaks down to horizontal A. Horizontal, I'm going too quick, come on man. Horizontal A, it's a horizontal force here, plus M1G minus horizontal B equals M1 x double dot 1. Then for the vertical, we have plus VA, there's no force at this, minus VB equals M1 y double 1. And then we have the sum of the torques at the CM, the I at the CM times phi double dot. And that means at the CM, the torque. So we have 4 forces. So all forces give a contribution. The thing had a length of L, so that should be in the free body diagram, right? And of course this is in the middle, L over 2. This is in the middle, L over 2. And then, we have this angle. Let's, for Pete's sake, put in that angle. That makes it easier. So that's phi 1. And now we have to take all the action of all these forces. So it's force times distance. If this is L over 2 and this is phi 1, then we need this arm. And that's the sine of the angle, right? Well, for sine phi 1, I'm gonna use a shorthand notation called S1, because otherwise I have to write so much. So this is shorthand. Okay, with the shorthand, well, HA is in that direction minus AB, and is it positive? Yeah, this is positive, so they are both contributing positively, so it gets HA plus HB times L over 2 times sine 1. That's plus. And then the V, the verticals, they give a counter-rotating torque, minus VA plus VB L over 2 cosine phi 1 equals Y1 phi double dot 1. And of course, likewise, go away. Likewise for body 2. Let's put this a little bit out of the way. Yeah. Oh, no, that doesn't help. That does help. Okay. Now for body 2, we're going to do exactly the same thing. Again, sum of the forces is mass times acceleration. Body 2, we have to keep that in picture, yeah. So that's a horizontal force in B plus M2G equals mass times x double dot 2. Then the vertical ones is VB. That's all. Okay. So the vertical acceleration here is only driven by this. Yeah, that makes sort of sense, right? And then the torques, well, we now only have two forces acting as a torque thing on this. So this is phi 2, right? So that would be then the horizontal in B, L over 2 times the sine of 2 minus VB L over 2 cosine 2 equals I2 pi double dot 2. Okido. Well, these are the 6 equations of motions in the unknown accelerations, right? Unknown accelerations being x double dot being x double dot 1, y double dot 1, phi double dot 1, x double dot 2, y double dot 2, and phi double dot 2. So these are unknown accelerations. Yeah. Are these really the unknowns? Do we know what all the forces are? Well, we know what the gravity forces are, but we don't actually know what the constraint forces are. So not only do we have unknown x, but also unknown joint forces. Let's call them joint forces. And the joint forces are, in this case, HA, VA, HB, and VB. And that makes the total of unknowns, so the total is 1, 2, 3, 4, 5, 6, 4, 10 unknowns. 10 unknowns. And how many equations do we have? So let's do some counting. We have only 6 equations. So 6 equations in 10 unknowns. How is it going to work? can we, well, the 10 is a bit sloppy. Let's change the 10. Delete. In the 10 unknowns. So 6 equations for 10 unknowns. I mean, they are linear in the unknowns, so that is good. It's not nonlinear equations, but how do we solve 10 unknowns from 6 equations? Well, I always call it a Cole-Porter problem. It's a Cole-Porter problem. Now, why is it a Cole-Porter problem? Well, because there's this song by Cole-Porter, and it goes like this. In olden days of silken stocking, showing a leg was shocking. Now heaven knows, anything goes. So the problem is, anything goes. We have an infinite number of solutions. Oh, infinite number of solutions. The infinite symbol is not so nice. Okay, infinite number of solutions. And that's not good, of course, an infinite number of solutions. So we are missing something. And what are we missing? Any ideas? Remember that we did cut the parts, right? So what we did is we had a system. So let me get back. We had a system like this. And then we applied scissors. And then we got 2 separate systems. Like this. Now, how do we get back to this system? So you want to get back to this system. And there's only one way, and that is with, we call that glue. So, if we have the separate system, let's draw this here. This is not so nice. Let's rotate it a bit. Yeah, like this. If we have the separate system here, by cutting it up, we need glue. And then we're back at the original system. So we have the equations of motion for this. We have the EOM. Now, what is the glue? And in our case, the glue is actually pretty simple, because that is the relation that the parts belong together. Or in other words, let's start with the first simple glue. So we had the support here. Remember? Support point here. And then we cut the body loose. So we had something like, we did something like this. And then here we have this body, but this body should be connected, right? They should share the same point. And how do we express that? Well, if this was the body, and this was x1, y1, phi1, this position, and the length of this guy was L, then we want to say that this point coincides with the origin here. So we have x and y here. So the glue is actually saying, oh, xa is in 0 and ya is in 0. That is the glue in this case. So this yeah, I can draw, let me draw the glue here. I sort of like drawing glue. Yeah, how do we write glue here? Okay, so this is the glue. Or in mathematical sense, what is the glue? Well, we can calculate this position given this position, right? So we can say x1 minus L over 2, what is it? Cosine 1 equals 0. And then the other one is y1 minus L over 2 sine 1 is 0. and this glue, these are actually what we call the constraints. And likewise for the other joint, right, we can write down these two constraints, and then I have to draw it. So I have this point B, and this was body 1, and this was L, remember, and then here we have body 2, and this is also point B, also this, oh, forget about that one. This was also L, and then we have to glue this together. And how do we glue that? Well, we can calculate what the position is of point B relative from starting from body 1, and that should be equal to the position of point B when we start from body 2. Or in other words, in components, we can say, oh, x1 plus L over 2 cosine 1 should equal x2 minus L over 2 cosine 2. And likewise with y1 plus L over 2 sine 1 is y2 minus L over 2 sine 2. Now, I usually like to write this as constraint is something, is 0. So I like to rewrite that as x1 plus L over 2 cosine 1 minus x2 minus L over 2 cosine 2 is 0. And then here y1 plus L over 2 sine 1 minus y2 minus L over 2 sine 2 is 0. And now, lo and behold, how many equations did we formulate? We now have 4 constraint equations. These 4 constraint equations together with the 6 equations of motion form our set of equations. However, so the 6 equation of motion plus the 4 constraint equations are able to solve our 10 unknowns. There's one slight problem, and that is the constraint equations are not in the unknowns, they are in the position. And we need actually the constraint equations in the accelerations. So we need not formulate the constraints on the coordinate level, but we need it on the acceleration level. But that's super easy, of course, because you just take the equation and you just differentiate it twice with respect to time. So let's take the first one. So we say, well, x1 plus L1 over 2, what was it? A cosine, and now I write it out to be clear, is 0. Then we differentiate d dt with respect to time, and then we get x dot 1. Well, the derivative of cosine is minus sine, so minus L over 2 phi dot 1 sine phi 1 is 0. So that is the constraint in the velocity, and you can even draw that, that's sort of fun. If you have here this body, and if you have then here a velocity, x dot 1, and you have an angular velocity, phi dot 1, and then you see, oh yeah, there's this, this velocity, phi dot 1 times L over 2, and then the total velocity of this point is the projection, of course, of this guy, and that is, of course, the sine of this angle, it's this small part, plus that one, that's the total velocity of this point, and that should be, of course, equal to the velocity of this point. It should be 0. Not enough. We have to differentiate that again to get it on the acceleration level. And so this is for the velocities here. Then we get x double dot 1, and now I first differentiate this one, L1 over 2 phi double dot 2 sine phi 1, and now I keep this constant and differentiate this, and we get minus L1 over 2 phi dot 1 squared cosine phi 1 equals 0. Now, and this is now finally our constraint equation on the acceleration. And of course we have to do that for x double dot 2, for the other ones, for the other 4 equations, and then we get our 4 constraint equations with all the x double dots, y double dots, and phi double dots. And then we can form the whole system of linear equations together. And how does that look? Well, of course it's in the book, but if we then form that together, then we have one big matrix we're going to make, and we have one vector. Let's start with the vector of unknowns. So the big vector of unknowns is of course x double dot 1, y double dot 1, phi double dot 1, x double dot 2, phi double dot 2, and then we have those 4 forces, HA, VA, HB, and VB. Those are our unknowns. And it's all linear equations, so that should be doable. Then the first set, let's do a division here, something like this, and this should be about rectangular. So this is 2 blocks, so something like this, right? So the first part is of course, this set is just equations of motion, EOMs, and this is just constraints. 6 equations of motion and 6 constraint equations. So the equation of motion is of course mass times acceleration, and then plus some terms of these forces. And for instance, the first one, m1 x double dot 1 plus HA plus HB equals m1g. 1g, and then here 1, 0, 1, 0, right? 8 plus HA plus HB equals this. Second equation, m1 y double dot, and then we get plus, oh yeah, this should be a minus 1, sorry, and then a minus VB, and then the third one is y1, this guy, and then I'm not going to write that out, that's with L over 2 and sine and cosine, that's too much. And on the right hand side 0 and 0. And you can continue, m2, m2, i2. Not so interesting for now. Well, anyway, this I know by head, 0, 0, 1, 0, 0, 0, 0, 1, and this is, check it out. Then the constraint equations, well, they only have to do something with the accelerations, with this part, and nothing to do with the forces. So here we have all zeros. Oh, here we, sorry, it's not a 0, this was m2g00. This is all zeros. Then we have acceleration, and then here we have also terms. Well, let's start with the first part. The first constraint equation was x double dot 1, and there was no phi double dot, y double dot 1, and then there was something like L over 2 cosine 2, and then the rest is all zeros, right? 3, 0, because the first constraint was only about point A, etc., etc. Finally, if we do then a shorthand notation of this guy, then how does that look? Well, it looks something like we have a mass matrix here, we have a matrix A here, we have zeros here, we have a matrix B here, we have accelerations here, we have constraint forces here, and then on the right hand side we have applied forces, and we have some terms here with which are in phi square, etc. But we have a nice set of linear equations. 10, this is 6, this is 4. 10 by 10, this is also 6 by 4. So should be able to, if this is regular, we should be able to solve it. I'm a bit scary because there are zeros here, but on the other end there are no zeros here, or at least I think. So maybe in the process of solving this we will get numbers on the diagonal and then we get a solution. Anyway, that compromises the content of the lecture for today, and I hope you have enjoyed this short enlightenment to the textbook. I now finish this part, and then I immediately move over to the Q&A in Zoom. So For those who have questions and who want answers, do I have questions? I don't know. Who have questions and maybe I have the answers, go to the Q&A. Thank you for attending, and see you next week in the lecture. Stop recording.